Knowles CELIS, AFP, Getty Images. One single-use plastic bag takes at least 450 years to degrade. Give Miranda Wang 3 hours and she can reduce 10 of them into liquid. Wang is the first to discover a chemical process that tackles the end of life of plastic. She first learned the scale of the problem in 8th grade with her friend, Jeannie Yao, when they visited a city waste recycling plant in Vancouver, Canada where they grew up. That's when we learnt that even plastics that are put into a curbside recycling bin end up being exported overseas in developing countries where they become ocean pollution, she says. Since the 1950s, 8.3 billion tons of plastic has been produced. It's now found in toys, car parts, in donor organs and in the oceans. Because of the centuries-long degradation period, most of it still exists, 6.3 billion tons of it as waste. While many are trying to curb the inconceivably big problem of plastic pollution by collecting it from oceans and placing bans on certain products, Wang says it is commendable, but it is not enough. If we can not just outlaw plastics altogether immediately, if we're always going to produce this plastic, what do we do about it? How do we pragmatically handle it? Recycling plastic today is a mechanical process. It is sorted by color, shredded, cleaned, and melted. But this is limited to only certain types of plastics: PET, used in water bottles, and HDPE, used in milk jugs. The 5 other types of commonly used plastics usually contain colorants and plasticizers that mean they cannot be recycled. Adding to this is that most plastics thrown away are covered in food and grease and so are automatically rejected by markets with strict quality standards. Otherworldly wild are raging across Manchester Mall, and these are the plastics Wang has her sights on. Our technology can turn these dirty films that have food or dirt or any kind of grime or any kind of contamination on it, and we turn this material into a combination of 4 different kinds of chemicals, called organic acids, says Wang. In 2015, Yao and Wang, while they were still at college, founded BioSelection. The startup was based on their discovery of a bacteria that has evolved to eat plastic. But it did not take long to realize that the bacteria would always prefer to eat whatever food contamination was on the plastic surface, and when it did eat the plastic, the speed at which it could digest it was far too slow. They shifted their thinking towards using chemicals with a focus on film plastic. Used for plastic bags or food packaging, it is made from the extremely cheap material polyethylene. In the US, it is the #1 produced plastic by quantity, above PET plastic created for plastic bottles, and more than 97% of it is not recycled. Film is the worst type of plastic because it's so easy to catch surface contamination, says Wang. You can have such a small amount by mass, by weight of plastic, and it's entangled and wrapped around everything in the waste bin and it just catches all the liquids and the oil. Rather than using bacteria to break down the plastic, Wang uses a clear liquid catalyst. To prove that it works, she used plastic waste taken from a city waste plant in San Jose. We shred this plastic, we put it into a flask and then we add our liquid catalyst, she says. It is a relatively conventional chemical process, something she prioritized during its design so that it can be scaled. The reaction occurs at 120 degrees Celsius in common glass equipment with no added pressure. While the surface contamination on the plastic bathes in the catalyst, it does not react. The plastic itself, made up of a long carbon chain of polymers, destabilizes and collapses on itself to create other chemicals with 4 to 7 carbons in the chain link. So instead of having one extremely long carbon chain, it forms many chemicals with shorter chains with 4 to 8 carbons in size, says Wang. That is what is in the liquid at the end of the reaction. The smell of dead sharks is helping to keep surfers safe from attack. The liquid catalyst is then boiled off and recaptured by the system, recovering it so it is constantly used to break down the plastic and cause a chain reaction. The chemical identity of the content changes. That is why the plastic becomes a liquid in the end, says Wang. It is not a plastic liquid, it is a chemical liquid, because the plastic polymer has changed into chemicals. After this, another chemical separation can be done to turn the liquid into a white chemical powder. One of these chemicals is adipic acid, a precursor for materials like nylon and polyamines used in fashion, for electronic parts and in the automotive industry for car parts. Our vision is to transform the polyethylene, which right now does not have any down market value once it's consumed and is used for one life cycle, and we turn it into a chemical that is of the same quality as what is immediately made from petroleum, adipic acid, says Wang. This first helps us not allow film plastics from becoming pollution, and second is that it actually displaces petroleum from being needed to be extracted to make new materials. The ecologists who think moving to cities will save the planet now, bioselection is ready to scale. From the initial 10 plastic bags in a 500 milliliter flask breaking down in 3 hours, she is creating a continuous 5-liter system. In October, they will conduct a demonstration pilot at a plant in San Leandro, California, where over 3 months, 17 metric tons of plastic film waste will be converted into 6 metric tons of organic chemicals. Crucially, it will also provide much-needed data about how the system will work at a larger scale. At the moment it is impossible for us to know exactly how our reaction will work on an industrial scale, what the exact economics will be, says Wang. In 2019, they plan to build an even larger machine that will process 5 metric tons of plastic waste per day. This will be standardized, replicated and transported anywhere in the world where there is a lot of waste, where it can be plugged into a wall and left to run. The next move is to expand beyond film plastics. We can actually deal with any kind of polyethylene, even if it's in a rigid form. As long as it's shredded, we can use it. But there are also opportunities in polypropylenes that we're interested in, she says. Wang sees plastic pollution in 2 parts. First is the collection and centralization of the materials that are the problem. Especially in the context of oceans, like how do we get that back, she says. The other is what to do with the material once it's been collected. Ocean Cleanup is bringing the plastic back from the ocean. What is he doing with that? I've seen the waste he gets. The plastics he's getting look like sand a lot of the times. He can't sort that material, so what is he going to do, says Wang. There's no market for that material. She says while organizations like Sea Shepherd and Plastic Pollution Coalition are doing good work, much of the time they do not have any other option but to send the plastic they collect to landfill. It is awful because these people are so committed and ocean cleanups are so hard to do, but all we're able to do today is to move the plastics from one place to another because there's no other way of destroying it, says Wang. The other issue is too much of the work today in this space, like others who are looking at bacteria to break down plastic, is too slow and too theoretical. They're only able to break down less than a couple milligrams over 24 hours. They're using polyethylene strips from a plastic bag that are completely clean, she says. City trash is not clean. This, she says, is simply not good enough. We need technologies that are actually robust enough to handle those materials as it exists in our world today and not as some theoretical curiosity project. We're at a place that if we don't make substantial changes by 2050 there will be more plastic than fish in the ocean.